This section is about exponential functions. And we'll be looking at those. Exponential functions are any functions that are of the form f of x equals a to the x, where a is a number bigger than 0. Bigger than 0. I'm sorry. Excuse me here. It's not bigger than or equal to, it's bigger than 0. That's what I said. Bigger than 0, and a cannot equal 1. Main reason a can't equal 1 is because then you'd have 1 to the x, and 1 to the x is always 1, so that's kind of boring. So we don't worry about that. But this is what a basic exponential function looks like. A is known as the base. The base has to be greater than 0, and you have to be not equal to 1. So next I want to talk about the graphs of an exponential function. So these are the different graphs. A bunch of them are drawn in here. This is 10 to the x, 4 to the x, 2 to the x. Notice that 1.5 to the x, 2 to the x, 4 to the x, and 10 to the x all are increasing, whereas 1/4 to the x, 1/2 to the x are both decreasing. So notice that these bases, 10, 4, 2, even 1.5, are all greater than 1. 1/2 and 1/4 are less than 1. So that's kind of an important piece for us to know about graphs. So I want to talk a little bit about these graphs and what's going on with them. So what I notice is that there's a couple of things I want you to talk about. I want to talk about the domain. The domain of an exponential function, every exponential function is, well, if I look at these graphs, I don't see any places where there's any issues. There's no values I can't be. So that means my domain is all real numbers. You can either write it as negative infinity to infinity, or you can write all real numbers. It's up to you. That's a little long to write, so mathematicians have a symbol for all real numbers. It looks like an R with a fancy little line on the front of it. The range, again, remember the range are the y values. So I'm looking at this, what y values can I take on? I look at this and I notice that every single one of these graphs never cross this horizontal x-axis. That means that all the y values are bigger than 0. So the range is actually from 0 on to infinity. 0 is not included because you can't raise a number to a power and get 0, but it's always that way. You can also write it as y is greater than 0. Either way. I prefer the interval notation. A couple other things about them that I want to point out about all these graphs is the X-Intercept. If you look at every single one of these graphs, none of these have shifts, none of these have reflections. They're all just basic graphs, 10 to the x, 1/2 to the x, 1/4 to the x, and so forth. But every single one of them goes through this point 0, 1. So they all have a y-intercept of 0, 1. An x-intercept, well, it never crosses the x-axis, so it can never have an x-intercept. So the x-intercept is always for these none, whereas the y-intercept for every single one of these is 0.01. All of these have what we call a horizontal asymptote. We will never cross this axis, so we call that a horizontal asymptote. It's not that it never crosses, it actually also gets closer and closer as x goes closer and closer, or in this case, closer and closer to negative infinity. We're going to get closer to this x-axis, but we're never going to cross it. On these two, as x gets bigger, going to positive infinity, we're going to get close to it, but we're never going to cross it. So that actually is the definition of a horizontal asymptote. So all of these have an horizontal asymptote of the x-axis, or y equals 0. Notice they don't have a vertical asymptote because there is the domain is all real numbers. The other thing to notice is that when a was greater than 1, we were an increasing function. And when a is less than 1, we were decreasing. The next thing I want to point out, and I'm actually going to add a page in here, is laws of exponents. So the law of exponents, what they actually, just as a reminder for you, because we actually need these a lot when we're starting to do some calculus work. A to the x plus y is a to the x times a to the y. A to the x minus y is a to the x over a to the y. You're used to seeing them as a to the x over a to the y is a to the x minus y. It doesn't really matter the order, but we actually deal a little bit more with starting with them on this side and separating them out. Another one that you've seen common is a to the x to the y is a to the x times y. And another one is if you have the same basis, a times b to the x, you can do this as a to the x and b to the x. So you can separate those out. That also will become very important to us. One more that actually is really important to us is a to the negative x. That is actually 1 over a to the x. So this is actually one that's really important to work with, and we will be working with that one too. Normally, again, we start with this one and go to here. In the past, you've been told don't have negative exponents. Actually, in this class, we like negative exponents. So we actually probably most likely want to start with 1 over a to the x and write it as a to the negative x. Another thing I want to point out is that here is the graph of 2 to the x, and here's the graph of x squared. X squared grows up, it's increasing, but if you notice 2 to the x increases much, much, much faster than a to the x is. So for large x, x 2 to the x, or actually any a to the x, is much, much greater than x squared. And that's true of anything. All exponentials are always going to be much, much larger than polynomials. The next thing I want to do is just show you how we can model. So if we have a function here, this is actually the population of, I believe, the United States from 1900 to 2000. We're going to go ahead and put this data into graphing calculator of some fashion. I'm going to actually use Desmos. I find Desmos a little bit easier than your basic graphing calculator. So what I need to do is I need to go into the graphing calculator, into Desmos, sorry, and I need to type this in. So here's the basic Desmos. I'm going to go into making a table, and I'm going to type in my x values. My x values start at 1900. Then it's 1910. Desmos is pretty smart. It notices when you do 1910 and 1900, 1910 that you want to go 1920, 1930, 1940. So you can actually just hit enter each time up to 2000. And then my y values are 1650, 1750, 1860, 2070, 2300, 2560, 3040, 3710, 4450, 5280, and 6080. And then I want to graph them, and I look at my graph and I can notice it goes from negative 1010 to negative 1010. So I'm never going to see these dots. So I need to come over here to this little thing that looks like a wrench. It's the graph settings. I need to change my axes. My x-axis could actually start around, let's do 1890. And then I'm going to go all the way up to, let's say, 2010. My y-axis, I'm going to start at 0 because we usually like to start the y-axis at 0. I think Desmos might have issues with this, but we'll try with that. And we're going to go up to, I don't know, 6200. These numbers, by the way, are in millions. So here's our graph. These are our dots. And if I look at this, it does have that basic shape of an exponential. That's really what's important, is understanding these basic shapes and what they look like. So we can see it does seem to have that, which means we can model that with an exponential. So what I'm going to do is I'm actually going to tell Desmos that I want to use an exponential function to figure this out. We have y1 as my one variable, so I'm going to start with y1. I'm going to do the tilde, which is on your keyboard. It's in the upper, it's the key next to the 1 key. It has a tilde on it. So I'm going to use that tilde, and then I'm going to go ahead and put in the basic function of an exponential, which is a times b to the, and we don't want to just put x, we want to do x1 because we wanted to use these x1 values. So we're using y1 and x1, and it'll actually create, it graphs it up for me. Model's pretty close. So we can now kind of test that this seems to actually model pretty good. And if I look here, it tells me my parameter values. So it tells me my a is 3.9 times 10 to the negative 10. So really, really small a value in front of here. And then my b is 1.015. So I could actually now write that down, and I actually now have a mathematical model to model this data of the population of the United States. All right, so I have that now. And the last thing I just want to mention in this section is the number E. The number E is actually the number, it looks like 2.718182 something, something, something. It goes on forever and ever and ever. And it does. It actually is an irrational number. So it's approximately equal to 2.718182. And then it does go on forever and ever and ever. So if you want to write dot, 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 you can. The approximately equal to kind of did that for me already, so I didn't really need the dot, dot, dot. But it does go on forever. It's an irrational number that goes on forever. And what I want to do is kind of talk about, you're going to see more about this number. And this is kind of a precursor to what we have. This line here is known as the tangent line. It hits the graph at one point, kind of follows the graph along the way, but only hits at this one point. The point in this case is the 0.01, because that's the intercept, so we're going to use that point. And if I use 2 to the x, the slope of this tangent is about 0.7. If I do the same thing with 3 to the x, again, it's still going to go through the 0.01, but it still use that 0.01, but now the slope of this line is 1.1. So that makes you think, well, if there's a slope of 0.7 and another one has a slope of 1.1, there must be some base, some exponential function that has a slope of exactly 1. And there is, and it turns out that happens to be the number E. So number E actually has a slope of exactly 1. It's the only function in the world, and that's why we care a lot about it and why we spend an awful lot of time with E. And it shows up a lot of other places, and you'll see another place when we get into the concept of something called limits, you'll see where the E actually can come from, how we can approximate it.